Hello, welcome to this video on volumes of solids with known cross sections. So just like the title of the lesson, in this video we are going to be talking about volumes with known cross sections. And what cross sections are just slices of a solid. And I always talk to my Math 3 students about just kind of envisioning that they're playing like Fruit Ninja, or you're like slicing through something, and that's the shape, that two-dimensional shape, if you were to slice through an object. Another example that I heard from Mr. Maestas is if you're like, imagine you have like a loaf of bread, like French bread, so good, right? And then you slice it into individual pieces, right? And that would be what a cross section is you're just taking one cross section of that object. So let's go ahead and get to the lesson. And this says, in geometry, you learn formulas for finding volumes of common three-dimensional solids, such as cubes, spheres, cones, rectangular prisms, and perhaps others. Calculus allows us to find volumes of solids whose bases are two-dimensional regions within an XY coordinate system, and the heights are formed by cross-sections, okay? And the types of cross-sections that we're going to be specifically working with are a square, rectangle, a semicircle, a triangle, and maybe even an equilateral triangle, okay? And those formulas are there given for you. If you are going to have to utilize these on the AP exam, again, they don't give you these formulas, so this is stuff that you're going to have to put into your brain, okay? And, I mean, the most common ones, again, would be like something like a square, a rectangle, right? Base times height. Semicircle, I mean, that's just half of a circle, right? So pi r squared cut in half. And then a triangle you should be familiar with. Equilateral triangle, I think if something that crazy was on the exam, they may give it to you. Fingers crossed. If not, then you just have to work with what you got. But I don't expect something like that. But again, I would take the time to memorize these. Utilize your flashcards. Okay, so how do we calculate the volume of a solid with known cross sections? Well, what we're going to utilize is the integral. I'm going to accumulate the area of an object, okay? And we have a couple of different approaches. And what I want to do is I want to show you kind of an example. I'll go to an example of number one, and then I'll come back to this. But kind of here's what we're talking about. So if I have a solid that has a base of the area underneath the curve shown, right? So that would be something like this. So this bottom piece is the base. And then what we have is cross sections that are a known shape. So and in this example that we're talking about squares. So what we're going to do is we're going to take slices of an object, and if this is a square, right, then the height has to be that same height. So imagine the height of the object coming out this much. Okay, and there's one square. And then if I wanted the cross section here, if this is a side of a square, right, the height is the same distance. Okay, so it looks something like this. And then in this area, again, here's one side, so then the height would look something like this. And what we get going on is a solid object, and you kind of gotta use your best to envision this, because I'm terrible at drawing, and I'm not going to rely on this. I'm going to show you guys an image, kind of like what a cross section would look like, and it would look something like this. So imagine, right, each image that you have, and this is a rectangle, right, but in between those areas is you have objects getting bigger and bigger and bigger, with that as a base. So how do we calculate the volume of that object? Okay, and like I said, we're gonna be utilizing an integral, and I just need to cover some certain areas. So if we're going to calculate the volume with a cross section perpendicular to the x-axis, okay, we're going to be integrating from a to b of the area of a function, so whatever the area of that cross section is, okay, times dx, okay, where dx is our width, and I would add this in. Dx is the width. Okay, for a cross section perpendicular to the y-axis, that is going to have a width of dy. Width of dy. And maybe you're asking yourself, like, okay, Schwarberg, like, what do you mean, like dx dy? Okay, and I'll take example 1. So it says find the volume of a solid whose base is a triangle bounded by the line y equals negative 2x plus 2, x equals 0, and y equals 0, and whose cross-sections are squares, which are perpendicular to the x-axis. So, like I said here, they tell us it's perpendicular to the x-axis, which means that if I was to slice this base into infinitely many cross-sections, which again are all squares, right? So they're kind of popping out, and they're squares, right? So they would look something like this. Okay, they're coming out. And the width here, this width is going to be delta x or dx. Okay, so that's the width. Now, what I need, not delta d, delta x. What I need is the area of a square. Well, if I want to calculate, and again, I'll go back over to here. If I want to calculate the area of a square, and I'll simplify it, we'll just look at this one right here. If I don't look at the area of this square, the area is this side times this side. So s squared. And in the formulas that we have, right, they tell us this, that it's s squared, okay? And that triangle embedded here, that's going to be this. It's going to be s, okay? So that is the length, right, of our object, and then it's going to have a height of s, so s squared. So that's what this is saying here. So the volume is equal to the integral from 0 to 1, right? And these are our limits of integration, so 0 to 1 of s squared, which is our area, dx, which is our width. So this is volume, and we're going to accumulate all of that volume. All right, so what we need, though, is I need to represent s in terms of x, right? I want my integral to be in terms of x. So, I mean, what is this distance if I was to calculate s? Well, I know that this line here, right, that this line is y is equal to negative 2x plus 2. And if I was to calculate this distance for s, isn't that height here? Isn't this y? So I can go ahead and I can plug in this, right? So this y is equal to s. That's going to be one of our side lengths. Whatever y is, right, that's the height of my square. Okay, the height here is whatever the y value is there. And then here, the height of this is whatever the y value is. So I'll go ahead and I'm going to substitute out s. So this becomes the integral from 0 to 1 of whatever s is. So s was whatever y is, and y is negative 2x plus 2 squared dx. Okay, and before I go ahead and integrate this, notice that this is a reverse chain rule situation. Okay, in order to be able to integrate this, I have to come up with our hook. And our hook in this situation is negative 2. So I'm going to have to go ahead and introduce that. So I'll introduce a negative 2. Actually, and I don't like putting it there. I've kind of since changed my habits. I like putting the negative 2 back here with the dx. And then I have to go ahead and account for that. So I'll multiply by negative 1/2. Okay, so this is equal to negative 1/2 times negative 2x plus 2 to the power of 3 divided by 3. Okay, and this is evaluated from 0 to 1. So I'll go ahead and compute this. So negative 1/2 times, if I plug in 1 here, we get negative 2 plus 2, that's going to be 0, right? 0 cubed over 3 minus, if I plug in 0, we get 2 cubed, okay, which is 8 over 3. Okay, and I'll go ahead and compute this. So negative 1/2 times negative 8/3. This would be a positive 8/3, or sorry, 8/6, which is 4/3. 4/3. Okay, so there is the volume of the cross section. All right, so let's go ahead and set up, but not actually calculate the other two situations here. So it says set up, but do not integrate integrals from volumes of the solid with the same base in example 1. So I have semicircles perpendicular to the x-axis. So now all of this distance here, right, is going to be a semicircle. So it's going to look something like this. Okay, and these are all just going to be a whole bunch of semicircles from here to here. So what I want to do is I want to go ahead and integrate, okay, from 0 to 1 of this distance. So I need to represent that value. Well, the area of a semicircle, and they give it to us, is 1/2 pi r squared. So 1/2 pi r squared. Okay, 1/2 pi r squared. And I want to integrate with respect to x. Okay, but notice I have a r. I want this to be in terms of x, so I need to replace my radius. Well, if this is a semicircle, okay, our radius is only going to be this distance. So essentially it's half of whatever y was. So 1/2 of y. Okay, so I'm going to go ahead and replace that. So we have the integral from 0 to 1 of 1/2 pi r squared. So again, the radius is negative 2x plus 2 divided by 2, which ends up being just negative x plus 1. So I can go ahead, I can plug that in. So negative x plus 1 squared dx. And you're done. So you're just setting up, so you don't have to do anything else. If you were, I would recommend pulling out the pi halves to get that value. Okay. All right. Part B. It says find the rectangles of heights 1/4 which are perpendicular to the y-axis. So we're given rectangles. I'm going to go back up here, and I'm going to erase this. And we want them perpendicular to the y-axis. So they're going to look like this. Okay. So I need to go ahead and calculate whatever this distance is. I know the width will be delta y, right? That's the width of it. The length is going to be whatever this distance is, which happens to be x. Okay, so this equation, right, is y is equal to negative 2x plus 2. So I can just go ahead and solve. Y minus 2 is equal to negative 2x. So x is equal to negative 1/2 y. That would make it plus 1 is equal to x. Okay, so that is that length, and then they tell us that the height is 1/4. Okay, so this is going to be the integral from 0 to 2. Now, why is the limit 0 to 2? Well, we're integrating with respect to y, right? So perpendicular to the y-axis, so that is 0 to 2. Okay, and now I'm going to go ahead. So my height is 1/4 times my length, which is x, but in terms of y, that would be negative 1/2 y plus 1. Okay, dy, which is our width. So height, length, and width, right, which is volume. Okay, so there is the integral. All right, so I'm going to go ahead. I'm going to pause this video, and I'll make another one for the next videos. If you're having a hard time visualizing these cross sections and the volumes that are made, please check out the Khan Academy videos, which are below. Sal Khan does a great job using his drawing techniques. My artist skills aren't that good, but check out his videos. He has a great job showing you kind of what these solids look like. All right, catch you in the next video. Peace.